Okay, in our previous Python session, we actually computed a smoothed image. And in this session, we are going to compute the x and y derivatives of that image. For that, let's first compute the x mask. So mask or filter x is basically numpy dot zeros. Just there are multiple ways of building that. Let me build it in this way, 2 by 1. That's the x mask. And this mask, actually x, at index 0, we place a -1, and at index 1, we place a 1. So with that, our mask x is ready, which if we filter the image with, we will get our x derivative image. So ix is equal to cv2 dot filter 2d, our image, which is image smooth, -1 for the depth, and the kernel is mask x. So that will give us our x derivative image. If you see the shape of this image, that shape will be exactly the same as the shape of the input image x, input image shape s. Oh, that's 3. These are 3 channels. Actually, I was working with just grayscale image, so let's just pick one of the channels as image smooth. So let me just change the image smooth here, because sometimes these grayscale images, they are saved in a way or read by Matplotlib in a way that the 3 channels are just replicated. So image smooth with just the first channel, and now we are really good to go with that. And that's the shape, and this is the shape for our image. And now we are ready to basically compute the y derivative. If you see closely, this mask for y is just a transpose of mask of x. So we need not to compute the mask separately. The mask of y is simply, here we can write here, mask y is simply mask x transpose. That's it. And then we have our y derivative, cv2 dot filter 2d, image smoothed image, the depth, and mask y. And with that, we now have our y derivative, which is exactly, it has the same shape as this one. Let me show you the x derivative and y derivative images, just like images. They are, although they are matrices with negative values as well, but let's try to visualize them as matrices. So plt.imshow ix cmap equals gray, and here you can see it actually highlights the horizontal or x directional intensity changes. Now if I just copy the code for subplotting, and I plot the x derivative and y derivative side by side, it may look like more. So x derivative for horizontal attenuation and y derivative for vertical attenuation, we can have these titles as well. plt.title x derivative, and similarly we can have y derivative. And yeah, so you can see here that the x derivative or the derivative in the row direction actually highlights the changes in vertical direction, whereas the y derivative, it actually highlights the changes in the horizontal direction or left to right direction. So these are our, actually, if I want to compute the gradient vector for any pixel, for example, let me compute the gradient vector for pixel 5,3, let's say 5,3, and that is simply the ix at 5,3, and then I have this iy at 5,3, and I can just arrange them in a vector form using maybe a NP array or list or whatever I really want. So for example, np.array, and that gives me the gradient vector for location 5,3. That's it. So gradient vector, that's the, in this particular case, the ix and iy for this particular location are both 0, although they're not 0 overall. Further, I can compute the gradient magnitude and gradient direction very easily, but that we will do in our next video, because before computing gradient magnitude and direction, I have to talk a little bit more about x derivative and y derivative in the context of Canny edge detection. So hope to see you in the next video.